Hello, welcome to this video, and today we're going to prove two very important derivative formulas. So first thing I'm gonna let's talk a little bit about derivatives. So derivatives help us know they help us understand how much a function is increasing or decreasing. So if I have a certain plot of a function, if I calculate the derivative at a certain point, which corresponds to the slope of the tangent of the function at that point, that will tell us by how much about how much it will increase if we go in very little steps in any direction from that point. So if we look here, it's a pretty small derivative, meaning that if we go into any side by a little bit, we won't see big changes. We will see changes, but we won't see any big changes in the value of it, of that point. But if we look, say, here, the tangent we can see is much bigger, meaning that as we move just a little to the left or to the right, we'll see much bigger changes in the value of the function at those points. And there is also an actual rigorous formula for it. So df over dx, which is the derivative of f, and with respect to x, is the limit as h goes to 0 of f of x plus h minus f of x over h. I have a whole nother video where I derive the formula and explain the intuitiveness behind the formula. But this is the definition of the derivative, and derivatives are very important in calculus. Not only just to understand how functions behave, although they are very important for that reason. There are also other very substantial things they're very useful for. And so we need to get a grip on how we calculate derivatives of complicated functions. So we can use this derivative to calculate simple derivatives, things like x squared, maybe things like x and squared, pretty much like polynomial things. And then when you think in things more complicated way, you can think about exponents, so 2 to the x, or maybe e to the x even, which has the property where its derivative is, where its derivative is equal to itself. And maybe you can then think about trigonometric functions, so things like sine x or cosine x. And these you can find the derivatives for with this formula. But then, how do you calculate the derivative for something like e to the sine of x squared? What do you do then? I mean, we know the derivative for the e to the power of x, sine of x, and x squared. But how can we combine those derivatives to get the derivative of this function? So is there even a formula for it? And if there is, how can we calculate it? So this is what we're going to do. And we're going to prove two properties. There are actually three important ones, but the first one is just addition, and it's pretty simple. We're going to prove the product rule and the chain rule. So the summation rule says that d of f plus g, so if we add two functions and take the derivative, you can just plug it into this formula, and you can very easily get this is just the derivative of f, just the derivative of f plus just the derivative of x. And this is easier to prove. I'll let you do this by yourself. But there are two very important rules that aren't as intuitive and as easy to prove. There is a certain trick needed to be used in each one of those proofs. So let's clear the board and do one at a time. Okay, now first thing we're going to do is the product rule, meaning that we're going to look at the derivative of the product of two functions. So we have no choice but to use the definition of the derivative. So this is the limit as h goes to 0. So all we did is substitute f times g into the definition of the derivative. So we plug in x plus h, subtract when plugging in x, and divide by h. Now we're going to use a nice clever trick, which is, because we're looking to separate individually f of x plus h minus f of x and g of x plus h minus g of x. So we can look at their derivative separately. Or a clever trick we'll use here is adding and subtracting the same value from the numerator. And that value will be f of x plus h times g of x. So we know this is the limit as h goes to 0. Now we will put these in brackets. So we have the limit as h goes to 0. Now we know, and we can separate this because we're separating a finite sum. So the limit of a finite sum is the sum of that finite limit of each term. Is the finite sum of the limit of each term. And then it's the same for the product. The limit of a finite product is the same as the finite product of the limit of each term. Meaning that we can look separately what this approaches and what this approaches, and here what this approaches and what this approaches. So here we can see that this approaches f of x multiplied by the definition of the derivative of g, and here it approaches g multiplied by the definition of the derivative of f. And I'm going to switch the sides. So I'm going to write this first and then this, just so it looks a little nicer. So it's going to be the derivative of f with respect to x. So df over dx multiplied by g of x. And then add on this, which is f of x multiplied by dg over dx. And that's a very nice rule. So the derivative of a product is just taking one term, taking the derivative, multiplying by the other term without the derivative, and then doing the same the other way around and summing it up. Just as a quick example, let's do the derivative of x sine x. So we know that, so what we're going to do is separate it by this rule. So I'll have dx over dx. So the derivative of x multiplied by sine x plus x times d sine x over dx. So we're multiplying x by the derivative of sine. And we know the derivative of x with respect to x is obviously 1. So this is going to be sine x. And we know the derivative of sine x with respect to x is cosine x. Multiplying by x, we get plus x cosine x. So something that would be really tedious to calculate with the definition of the derivative can now be easily calculated with this simple formula. So now let's erase the board and do the chain rule. Okay, now we're going to look at the chain rule. So here, instead of multiplying two functions, we're inscribing two functions. So g inscribed in f. So it basically means if we have the definition really of this function is we calculate g of x, and then we put that as an input for f, and then that output is f of g of x, which is also written like this, that of g which is inscribed in f of x. So f, this empty circle g of x, is just f of g of x. So that's just the definition of it. And then we're going to calculate the derivative of this. So now let's calculate it. Again, we don't have any tools other than just using the definition. So we have the limit as h goes to 0. Do we want to calculate this and find a nice formula for it using just the derivative of f and g? So what we're going to do is, well, we want to separate so the trick we're going to use here is, instead of adding and subtracting on the numerator the same term, we're going to multiply the numerator and the denominator by the same term. And that term will be g of x plus h minus g of x. So, and then we're going to separate the fractions. Now we know, again, this is a finite product of two terms, meaning that the limit of the entire product is the product of the limit of each term separately. So we already know what this will come out to be. This is just the derivative of g with respect to x, meaning that this is dg over dx. Then we're multiplying by the limit as h goes to 0. Now I'm going to write g of x plus h here in a bit of a weird way, but you'll soon see why. So I'm going to write it as f of g of x plus g of x plus h minus g of x. So all I did is add and subtract g of x minus f of g of x over g of x plus h minus g of x. Now, now let's see here. We can say that this is dg over dx. Now we replace g of x plus h minus g of x with epsilon, and we know epsilon goes to 0 as h goes to 0, meaning that this is the limit as epsilon goes to 0 of f of g of x plus epsilon minus f of g of x over epsilon. And now, just so everything is more clear about what this actually is, we are gonna let g of x equal u, another parameter u, and so we have dg over dx multiplied by the limit as epsilon goes to 0 of f of u plus epsilon minus f of u over epsilon. Now this is the definition of the limit of f with respect to u, meaning that this is dg over dx multiplied by df over du. But remember, we just set u to be g of x. And we did that just so everything is more clear about what this actually is, meaning that we can just replace this du with dg, and because u and g are just the exact same thing. They're both the same function with respect to x, meaning that we got the d of f, because meaning that we got d of f inscribed in g, of d of g inscribed in f. All it is the derivative of g with respect to x multiplied by the derivative of f with respect to g. Now this might seem a bit confusing about what this d of f over dg actually means, because so far we only worked with over dx. So let's do a quick example just so everything is clear about what this means. So let's calculate the derivative of e to the x squared over dx. Now first thing we have to realize is what function is inscribed in what function. So we can see two functions here, e to the power of something and something squared. So, and what is inscribed in what? Well, it's either we're doing e to the x squared, or we're doing e to the x all squared. Well, because that's the two functions we're seeing, and one is inscribed in another. So that's our two options. And we can see that in our option, x squared is inscribed in e to the x, meaning we replaced x squared with x in our function e to the x, meaning that our function f is e to the x, our function g is x squared. So what we want is d of x squared over dx multiplied by d of x e to the x squared over d of x squared. Now this is confusing. What this is, because x squared is our parameter, all we need is the derivative of e to the power of something. And then our parameter, instead of being x, is just x squared instead. We're looking at x squared not as our function at this time, but as our parameter for the function. So the derivative of x squared with respect to x is 2x and then the derivative of e to the power of something is e, and then when our is e to the power of that same something, it's the same function, and then when our parameter is x squared, this derivative would be e to the x squared. So our final result is 2x times e to the x squared. So just to make things more clear, this chain rule says you take the derivative of the inscribed function, so here it was x squared, and then you look at the derivative of the function that is inscribing, so here it's e to the x, you take its derivative, and then replace, each time you see x, you replace it with your function g, as if g is the parameter and not x. And then you're doing dg over dx, the derivative of g with respect to x, multiplied by df over dg, the derivative of f with respect to g. And then you multiply those things together, you get your final result of the derivative of your desired function. And those were the two rules. So let's write them here. So the derivative of f times g over dx is the derivative of f with respect to x times g plus f times the derivative of g with respect to x. So this is the product rule, and then d of g that is inscribed in f this is equal to the derivative of g with respect to x times the derivative of f with respect to g. I've explained both of these, gave an example, and these are the formulas most used for derivation. Obviously, there's also the formula of the sum and multiplying by a constant. Multiplying by a constant is essentially two functions where one of the functions is just the constant function. And the sum is very easy to prove that the derivative of a sum is the sum of the derivatives. At least for a finite sum. There are probably some cases maybe where it doesn't work for infinite sums, but for finite sums, the derivative of the sum is the sum of the derivatives, which is easy to remember. These are a bit more difficult to remember, and a bit more difficult to prove, which is why those are the ones I did in this video. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.